All right, so if you look at the probability chapter in your textbook, it starts off with a section which is just a review and revision of the probability material from first year. So what I'm going to do is just going to talk through some of the points that are made here in the book, and I'm going to talk through some of the examples, and then a couple of times jump back in to the first year book just where they have cut out the examples for space from this book. Okay, so the first thing that they've got here is the idea of the fundamental principle of counting. And they kind of express it here as a rule. If one event has m possible outcomes and the second event has n possible outcomes, then the total number of outcomes is m multiplied by n. That might seem a little bit confusing and it mightn't seem familiar, but if we look back at the example, this is what they're talking about here. So say Anna is going on holidays for a week. She's picking outfits and she has brought 3 pairs of jeans and 4 tops. How many different outfits can she wear? Well, she's got 3 choices of jeans and 4 choices of tops. So when she combines those, she has 3 multiplied by 4, 12 possible outfits combining a pair of jeans and a top. Okay, so that's what the fundamental principle of counting is about. It's about combining choices like that. All right, so let's say you're in a restaurant and there is 4 starters and 5 main courses. Well, there is 4 multiplied by 5, 20 ways you can combine those. There's 20 different meals you can have picking 1 starter and 1 main course. If I was to say 4 starters, 5 main courses and 3 desserts, then the number of choices would be 4 multiplied by 5 multiplied by 3, which is 60 possible choices. Okay, so that's what the fundamental principle of counting is. Just on the next page in the first year book, it's got an example where you are tossing a coin and rolling a die. Okay, so how many different outcomes are possible when you combine those 2 events? Well, when you toss a coin, it's heads or tails, so there's 2 possible outcomes. When you roll a standard die, it's 1, 2, 3, 4, 5, 6 possible outcomes. So when you combine the 2, it is 2 multiplied by 6, 12 possible outcomes, and they're listed there in a 2-way table. Just like the 12 possible outputs in this one is listed there if you want to go through them. If you don't trust the fundamental principle of counting, you can test it there by just counting on the lists they've given you. All right, so that's fundamental principle of counting. Probability deals with uncertainty and measures the likelihood of an event. We'll talk about that in a second. I'll just look at here first is the probability scale. So this is still an important idea. So probabilities go from 0 to 1. So they can't be lower than 0. They can't be higher than 1. Okay, so 0 is something which is impossible, so certain not to happen. And a probability of 1 is something which is certain, it's definitely going to happen. And then your kind of range of likelihoods from kind of 50-50 even chance down to unlikely and very unlikely up to likely and very likely are kind of in between those 2. Just be careful around using the word impossible and the word certain. So if I jump into say a question here in the book here. Yeah, so for each event below, mark the probability it will happen and mark this on the probability scale. So just to say it will snow in Ireland in July. Okay, so we can be very tempted to say that's impossible. Okay, because we probably have never seen snow in July, but I would say that is very, very unlikely. I wouldn't say impossible. There could be some freak weather event and it could snow in July. So just be careful around that word impossible. Okay, same one down here with C. So Ireland will win the next Soccer World Cup. We may be tempted to think that's impossible. It is just very, very, very unlikely. Okay, it's not quite impossible. Be careful with that word impossible. Okay. It will rain tomorrow. So I'm recording this in January. I think it's rained every day for the last week. It's probably going to rain tomorrow, but I wouldn't say it is certain. Okay, so I would just say it is very likely that it's going to rain tomorrow. Okay, so just be careful with the word certain and the word impossible. Okay, often when we say it in everyday speech, we just mean very, very likely or very, very unlikely. All right. Um, Now, next thing they cover in this kind of review in a higher level book is relative frequency, and I will just kind of highlight the difference between probability and relative frequency because they can seem quite similar. People can get them mixed up in their heads. Then they are kind of calculated the same way. Is why that happens. Probability is about future events where the outcome is uncertain. We don't know what is going to happen. Okay, but we can kind of calculate the probability. We can work out how likely each outcome is to happen. Relative frequency is about stuff that has already happened. Okay, and we are counting the outcomes. Okay, so let's say if I was to roll a die, what's the probability of it landing on a 4? It's 1/6. Okay, so it's 1 in 6. There's 6 possible outcomes. Only one of them is 4. So it's a 1 in 6 chance that if I was to roll a die, it will come up as a 4. If I roll a die 10 times, okay, so I've just rolled a die 10 times and it's come up on a 4 3 times out of that 10, say. Well, then the relative frequency of a 4 was 3/10 or 0.3 or 30%. Okay, so relative frequency is about you've actually done the trials, you've actually done the experiments, and you're just counting stuff that has happened. Probabilities then, as I say, making predictions about the future. All right. We'll see in a second then that we can sometimes use relative frequencies to calculate probabilities. Okay. As I say, that's an example we'll see shortly. Point 5 then will come, yeah, the rest of these ones then we'll just come to and go through as we work through some examples. All right. So just down here, when you roll a die, what number is most likely to come up? They're all equally likely on a fair die, okay? So it's a 1 in 6 chance of each outcome. If you roll a die 720 times, how many 5s would you expect to get? Well, you would expect it to land on a 5 1 in 6 times. So 1 in 6 or 1/6 multiplied by 720 is you would expect 120 5s. All right, so you can use probabilities to make predictions about the future. Example 2 here, the probability that Tom scores a goal in a match is 2/3. What's the probability he doesn't score? Well, there's only 2 possible outcomes there. He scores or he doesn't. Okay, so those 2 outcomes should add to 1. Okay, so if you add together all possible outcomes, the probabilities of all possible outcomes, they should add to 1. So 2/3 plus the probability he doesn't score should equal to 1. So it's a 1/3 chance that he doesn't score. Okay, so the probability of something not happening is 1 minus the probability that it will happen. Going up to this example here then, so Joe tossed the coin 300 times and threw 164 heads. Anna tossed the same coin 400 times and threw 235 heads. Joe and Anna think the coin may be biased. Give a reason why they think it may be biased. Well, they think it's biased because you would expect it to be ahead 1 in 2 times, so half the time. So Joe is expecting 300 multiplied by a half. He's expecting 150 heads. He gets 164. Anna is expecting 400 multiplied by a half, 200 heads, and she gets 235. So both of them have got more heads than expected when they tossed the coin. Okay, these are relative frequency calculations, the 164/300, the 234/400, because it's something they actually did. They actually did toss the coin over and over again. Okay, the 1 and 2, I'm saying that's a probability. That's what we think it should be. So that's why they think it may be biased. She uses this to work out the probability of throwing ahead with that coin. So what does she do? She adds up that between the two of them, they tossed a coin 700 times, and 235 plus 164, they got 399 heads. So 399/700 is 0.57. Okay, so the relative frequency of getting ahead based on that experiment is 0.57. So that's a relative frequency because they actually did it. Okay, they tossed the coin 700 times. So that's why that's a relative frequency. Okay, the probability I would expect is 0.5. Okay, now I wouldn't be confident saying that that coin is biased quite yet. Okay, and I would be cautious in any exam question about saying a coin is definitely biased. Okay, so you would expect zero point 0.5, you get 0.57, or you would expect 350 heads, you actually get 399. So it does seem to be throwing up more heads than possible. So you would say that the coin could be biased because you're getting more heads than you would expect. But to say for sure if it's biased, I would need to do a larger number of trials. So this kind of sentence here. Okay, so you would need to roll that coin, say 7,000 times or 70,000 times. So way more times before you can confidently say that it is biased. Okay, like the example would be if you were to toss a coin 10 times and it came up heads 6 times, you wouldn't say, oh, this thing is biased. Something's been put into this coin to make it land on heads more times as possible. We understand that when we toss a coin 10 times, it could land on heads 6 times or 7 times or 8 times. And we're not quite saying that, oh, this is an unfair coin. Okay. To say something's unfair like that, we need to toss it a really, really large number of times. Okay. So I would say anything that comes up in an exam, I would be covering off that point that I would like to do more trials before saying it's biased. All right. So just moving on to this example 4 down here, which is about using relative frequency to estimate probabilities. Okay, so in this example here, the colors of 500 cars that pass a particular set of traffic lights during a 2-hour period are recorded by a group of students, and there's a few questions about it. Okay, so without collecting that data, okay, without kind of standing there at the traffic lights and counting the number of red cars, blue cars, etc. If I just asked you, what's the probability that a car is red? Okay, without collecting this information, we don't know. Okay, we can say what's the probability that a car going past a set of traffic lights is going to be red. Okay, there's no kind of natural, easy probabilities attached to that, like there is, say, a die. There's 6 outcomes. It's a 1 in 6 chance of each. A coin. There's 2 outcomes. It's a 1 in 2 chance of each. The probability of the car that will drive past you will be red doesn't have a kind of natural, easy kind of probability attached to it. Okay, so what they've done here is they've actually collected data. Okay, so they've stood there, they've counted the color of 500 cars, and they're going to get the relative frequency of each color. Okay, so of the 500 cars that went past, 70 are red, 100 blue, 45 yellow, etc. First thing I'm asked to do is the number of black cars. Well, I'm told it's 500. Black is the only one that's missing, so just fill in the missing number there. That makes it add to 500. Part 2 then, calculate the relative frequency of each color and write these into the table. Well, there's 500 cars and 70 were red, so the relative frequency is a 70 over 500. And just write it as a decimal or a percentage then. The relative frequency of blue is 100 over 500, which is 0.2. The yellow, 45 over 500, and write it as a decimal or percentage, etc. Okay, so I'll just move over to the table actually fully filled out. So there's all my relative frequencies calculated. Okay. Part 3 then suggests a method to check that your relative frequency calculations are correct. Well, they're all the possible colors. They're all the colors I found. So all my relative frequencies together should add to 1. Okay. So if you add those together, they should add to 1 or 100% if you were doing it as percentages. Part 4 then, what's the probability that the next car to pass the light is red? So like I said, if I asked you this without doing the relative frequency calculation, you wouldn't know what's the probability a car that goes past is red. But now I know that I stood there, I counted out of 500 cars, 70 of them were red. So there was a 14% of the cars that went past me were red. So if I'm making a prediction about the future, then I would say, yeah, it's a 14% chance that the next car to go by is red, a 0.14 probability. Okay, so I will finish this example off and do the rest of it then in the next video.